Goal programming problems still have a single objective function, but multiple objective linear programming problems have more than one objective function. To tackle these problems, we must determine target values for each goal or objective, and we do this with a Minimax approach where we aim to minimize the maximum value of an objective. Let's dig into an example. Blackstone Mining operates two coal mines in extreme southwestern Virginia. They need to produce 48 more tons of high-grade coal, 28 more tons of medium grade, and 100 more tons of low grade. The details for each mine are illustrated in this table. We want to figure out how many shifts or how many months of shifts need to be added, but we also want to minimize production costs, minimize gallons of toxic water produced, and minimize the number of life-threatening accidents. With this data in hand, let's walk through the process of setting up this multiple objective linear programming problem. First, we define our decision variables. These are the variables that we're going to have Solver modify for us. So X1 is the number of months to schedule an extra shift at the Wythe County mine, and X2 is the number of months to schedule an extra shift at the Giles County mine. So we will have Solver adjust these values. These will be the green values on the sheet, so to speak. Next, we define the objective. We have three objectives. We need to minimize production costs, minimize toxic water production, and minimize the number of life-threatening accidents. Next, we'll define our constraints. We know that we're required to produce 48 more tons of high-grade coal, 28 more tons of medium-grade coal, 100 more tons of low-grade coal, and we know that the number of shifts can't take a negative value. We can't have a negative number of shifts in this case because we're increasing production. Although in some staffing scenarios, negative values may be possible when looking to find shifts to cut, for example. If we have target values for our goals, we can use them in the model, or we can solve, in this case, three separate linear programming problems, independently optimizing each objective to find the optimal values for each goal before running Solver to estimate the months to operate. So that's what we're going to do next in Excel. And this slide is an illustration of the different elements and formulas in the spreadsheet. And this is an overview of the settings in Solver for the example provided. So I've opened up the spreadsheet, and you can see that we've got our decision variables, the months to operate the Wythe and Giles mines, as well as fields for our objectives. Here we're using the sum product of B8 and C8, so these values, the cost per month for each of the mines, and our decision variables, and that formula is copied down the column. And then for our constraints, we use the sum product function again, and now we're using B13 and C13, so the amount of high grade coal produced at that mine, and the decision variables, again, the months to operate, knowing that we need to hit this requirement, and that formula is copied down for medium grade and low grade coal as well. So if we first need to find out, so to figure out target values, so for our three different objectives, we can start with production cost. So I'm going to open up Solver, and my first objective is going to be D8, cost per month. This is the production cost. So Wythe is $40,000 a month, and Giles is $32,000 a month. This is going to be our objective, and we want to minimize our cost per month. We'll do this by changing variable cells B5 and C5. And like I said, the shifts as a constraint must be greater than 0. And then we also have our constraints for high grade, medium grade, and low grade coal produced. So our values in column D must be greater than the required values in column E. And this is a linear programming problem, so we use the simplex LP method. I'm going to click solve. And the value we have when we optimize cost is 244. So I'm just going to type the goals here, or the objectives, goal, objective, to save them. What you can do is copy the sheet and evaluate each of the different objectives, but we'll do cost is 244, and then we can do the same thing with toxic water produced. We go back into solver, and now we change our objective from D8 to D9, and we solve for it. And we find that our toxic water value, when optimized, we can get it down to about 6,950 gallons. And finally, let's evaluate the optimal value for accidents per month. So we're minimizing our production costs, minimizing our toxic water, and minimizing our accidents per month. So now I'll change the objective cell to D10. I'll solve for it, and we get a value of 2. So these are our target values. These are when we can optimize for our individual objectives. This is what we get. And we see that, for example, when optimizing accidents, we do satisfy all of our requirements. In fact, we produce a lot of high-grade coal, a lot of medium-grade coal, and we just meet our low-grade coal constraint. So this gives us the basic information of what our target values are for these different values. But as we've seen in other examples, sometimes there are different weights that we apply to the different objectives. Sometimes we might favor cost over toxic water production, but not over accidents. And we'll get into that shortly. So if we sketched out the results, the shape of the feasible region would look like this. We see that the production costs are optimized at $244,000, toxic water production at 6,950 gallons, and accidents at 2. And this slide just reviews those goals again. The Minimax objective can be used to explore the boundary of the feasible region. So we want to minimize the maximum weighted percentage deviation from the target values for the goals. That effectively looks like the equation on the slide, but is represented in Excel by using the sum product function. It's just a linear combination of the decision variables. Let's add this objective to the Blackstone mining example and play around with weights, which, as experimented with before, can help us define our priorities. Mathematically, our new objective cell is considering this, but let's do it in Excel instead. So this is the Blackstone Mining Company example with weights, and this is a diagram of the example illustrating the variable cells, constraint cells, objective and variable cells, as well as the key cell formulas in that sheet. And this slide illustrates the settings you want to use in Solver to optimize your result. So now I've opened up the Blackstone example with weights, and there's a few more things going on in this Excel sheet than we had in the first one, but this one really enables us to make adjustments based on the specific priorities of the company producing the coal. So we still have our same decision variables, our months to operate, but we now have our total costs, total toxins, and accidents per month. We use the sum product function there. It's structured the same way as in the previous Excel spreadsheet, but now we have a target value, and this target value, these are the values that we calculated on the previous sheet, where we were able to first optimize production costs per month, then we optimized toxins per month, and then we optimized accidents per month. And then we add in, when we're working with the weights, the percentage deviation from the target value, and that is calculated in this case by subtracting the total, the target value from the total and dividing it by the target value. When you're doing the opposite, when you're trying to maximize something, you subtract the total from the target value and divide it by the target value. And that's mentioned on one of the later slides, just as a reminder. So depending on the situation, you may flip around the numerator in this equation, and it's the same equation all the way down. And then here are the weights that you can specify. And the weighted deviation is F8, so the percentage deviation multiplied by the weight. And then we still have our previous constraints, where we need to produce at least 48 more tons of high-grade coal, 28 more tons of medium-grade coal, and 100 more tons of low-grade coal. And then our objective function is this Minimax variable. And what this does, because this is an objective function that actually doesn't have a formula in it, what it does is run through all of the possible values to minimize the maximum deviation in the model. So we can go into Solver. Our objective function is B18, and we want to change the value in B18 as well as the values in B5 and C5. By having it change B18, again, that frees up Solver to evaluate all of the possible ways that it can minimize the maximum deviation. And then we have the same two constraints that we had in our previous spreadsheet, that B5 and C5 must be greater than or equal to 0, and that the total for production costs per month, toxins per month, and accident per month, or rather the constraints for high, medium, and low-grade coal, the available amount must exceed the required amount, and then our weighted deviations must be less than or equal to the value in B18. So the weighted deviations in column H have to be smaller than the Minimax variable outcome. So let's click Solve and see what happens. Sometimes when you run Solver, it'll pull up another screen. So that was the previous spreadsheet, but now we're back to the weighted spreadsheet. And we can see when everything is equally weighted that we end up with a deviation of about 7% for production costs and accidents per month. But we're pretty close with toxins. But maybe you want to put a greater emphasis on cost. So maybe you'll make the weight 3, and you'll make the weight for accidents 2. I mean, you want to save money, but you also don't really want people to die, but you don't really care too much about the environment in this scenario. We can run Solver again. and we'll see what happens. Well, it takes us back to our old spreadsheet, but we can go back to our spreadsheet with weights. The Minimax variable is now bigger, and we see that the maximum weighted deviations are 15%. Whereas the unweighted deviation is only 5% and 7.5%, and then less than 2% for toxins produced per month. And we can see that as we adjust these weights, our months to operate change. But I urge you that anytime you make any changes to things like your weights or your requirements, always run Solver again. Just because you see a value change in your spreadsheet doesn't mean that it's the optimized value. So, like I said, if you see something change, still run Solver again, just to be sure. And then, like I said before, Minimax solutions consider all of the values of the boundary, not just the corners. So some possible solutions include those indicated on this slide that are not at corner points. It's important to note that the solutions from using the Minimax objective are Pareto optimal, so there's no way to adjust them without making at least one individual or preference criterion worse off. Deviational variables and Minimax objectives pop up in a lot of places outside of goal programming and multiple objective linear programming. You might just start noticing them more often in reports, your work, and your life. And an important note on calculating percent deviation: when the goal is to minimize objective, it is calculated by subtracting the target from the actual value and dividing it by the target value. The target and actual values flip when the objective is maximization. Did I mention this is really important to note? It might come up in some homework, so just remember that. So you would flip those in the numerator. So the process in developing a multiple objective linear programming model is also a little more complex than regular linear programming, but the capabilities are much greater. Return to this slide as a reference if you get stuck wrapping your head around this type of problem. I hope this was helpful, and I'll catch you next time.